So let's begin today. So this is BVLSI. Let me connect the charger. Okay, this is BVLSI lecture number 50. Actually, there is some problem with my writing pad. That's why it's creating a lot of issue. Yeah, BVLSI lecture number 50. Let me put it to full screen mode. Okay. Yeah. Hopefully it should work. Yeah, it's giving a lot of problem. Anyways, let us start. So we are starting with the switching and the dynamic characteristics of CMOS. Actually, we have already covered the noise analysis, the noise margin analysis. So remember, for a CMOS inverter, we have done the following. We have calculated VIH, VIL, VOH, VOL, and VTH for CMOS inverter. Correct? And from these parameters we have calculated noise margin levels, noise margin high and noise margin low. So all this comes under the category of static analysis. Static analysis means not with respect to time. Static analysis of MOS inverter. That means these characteristics were like VTC curve, right? So it was voltage versus voltage. So we were analyzing the current voltage relationships, So these were VTC curves. So we have completed all this for the CMOS inverter. We have seen the numericals, the derivations, the working for the CMOS inverter. Today we are going to switch our attention to the switching characteristics. That means normally all the digital circuits which we are going to study in this semester, that is CMOS, resistive load, MOS inverter, NMOS inverter. Inverter is a digital circuit, right? So all of them have a capacitive load. There is a capacitive at the output. So let's say if you have a CMOS inverter over here, so definitely, surely, it will be connected to something. Okay, so it will be connected to a next stage or a series of chain, but normally its load is a capacitive load, CL. Got it? Okay. Now we have studied the MOSFET capacitance also in details. Yes or no? So we have this MOSFET. This is my PMOS. So this is my PMOS, and this is my NMOS. We apply a time varying input step to it, and we expect versus time. We have applied V in of time, and we have loaded it with the capacitor, and we will be plotting V out of time. So basically we are analyzing the behavior, how much is the delay associated with when a signal passes, when goes from 0 to 1. Okay, so here it is logic 0, this is logic 1. So the expected output of this will be, I mean, if I from 1 to 0, right? So how fast or how much delay it has, it is showcasing for it to change from 1 to 0. So okay, 1 to 0. So this we estimate in terms of propagation delay. Okay, we also have two more delays, rise time and fall time. So that also contributes to the the input slope. The input signal is also not a perfectly square wave. It will have a slant. So let's say if you see this waveform over here, it's not practical. Practically, we have a slight slope to it. So this is how a Wien signal actually looks like. Okay, it has a finite rise time and a fall time. Similarly, output will also have a finite rise time and a fall time. We have to need to estimate that. So let's look at, concentrate on this diagram. So here what we are doing is, here we have cascaded CMOS inverter stages. So let's say a single CMOS inverter is driving another CMOS inverter. Okay, so for a PMOS, I have all these capacitances. So which are the capacitances? I can see over here. VGD. So VGD and VGS are the gate overlap capacitances, which I'm marking in blue color. So VGD and VGS, these are the gate overlap capacitances. Okay, and then we have VDB and VSB. These are voltage dependent junction capacitances. We have derived it, right? We have solved numericals also of this. So these are voltage dependent. VSBP, VDBP, VDN, that means between drain and substrate of N type. N means N type MOSFET, NMOS. This. So the green color ones are voltage dependent junction capacitances. That means as the voltage between these terminal changes, the value of these capacitances are also dependent upon that switching. And we have total 4 and 4. Yeah. Right now the active ones are this. And then CG. CG is due to the tin oxide capacitance over the gate area. So this is also present at the gate terminal. So C init is the lumped interconnect capacitance. Okay, what do you mean by lumped interconnect capacitance? We'll see now in shortly. So basically, what will happen is all these capacitance will slow down our CMOS inverter. In short, okay. So how much slow or what effect it will have on the delay or the output waveform? That is what we are going to see. So we'll see how much delay these capacitances are providing or affecting. So if a pulse waveform is applied to the input, still the problem of analyzing the output waveform is fairly complicated, even for this relatively simple circuit. So right now, one CMOS inverter is driving another CMOS inverter. Okay, because of number of non-linear voltage dependent capacitance are involved. You see, four capacitance are involved right away. So to simplify this, we combine the capacitances seen in this figure number 1, okay, into equivalent lumped linear capacitances. So we say all these capacitances will be equivalent to a single capacitance at the output, which will be a combination of all of them. That is what do you call by lumped linear capacitances connected between the output node. So what we are saying is all these capacitances will be equivalent to a single capacitance. Here it is, CL. So the effect of all these capacitances will be included in this lumped output capacitances, which is a load capacitance, which is connected between the output node. So here is my output node, V out and ground. So then the analysis will become easy. So this combined capacitance at the output node is called as a load capacitance. So this capacitance we call it as a load capacitance. Getting it? Okay. So this is done because analyzing all of them together effectively and individually will be quite difficult task. So instead of that, we'll combine the effect in the output capacitance connected between the output node and the ground. All right. So let's go for that. So these are the things which I've already told you all. Some are voltage dependent, some are just overlap. So this is what I was talking about. Okay. Now we know that the MOSFET, PMOS and NMOS are a four terminal device, right? Substrate terminal and this VDD terminal also is connected. And this is the load capacitance which we were talking about. Okay. So this load capacitance is a combination of VGD, VGDP, VGDN, VDNP, VDPP, C init and CG. You remember two of the capacitance are missing. Why they are missing? CDBN and CDBP are yeah, yeah, CSBN. So here there are these capacitances are not present. I am telling you. I'll just let me mark it. So these capacitances are not present. This one and this one. The reason being is that here the substrate terminal and the source terminal are both connected to ground. So there is no VSB present over here. So here VSB is 0. Similarly here also the body effect or the substrate bias effect is 0. That's why this capacitance is not existent right now. Now there will be many circuits where this substrate terminal won't be connected to or body terminal won't be connected to supply for a PMOS and ground for a NMOS. In those cases these capacitances are included. So right now, this VSBN and VSBP are not present since VSB of volta voltages are zero. Okay, agree? So we get a combination of C load is a combination of all of these capacitances. Some are junction capacitances, some are area capacitances. So some have a direct formula Cox W into L. Some are voltage dependent also. So now the problem of analyzing the switching behavior can be handled more easily since we have a one linear lumped capacitance at the output. So just by finding the charge up and charge down times, we can discharge through one transistor, we can find the delay estimated to it. Okay. Are you following what we are saying, or you're finding it difficult to understand? Just let me know. Hello. You understanding what I'm talking about, students? Okay. So I think we have done one experiment on CMOS propagation delay estimation. So this is what it is. The propagation delay is low to high propagation delay. So that is tau. This is tau. P stands for propagation delay, low to high. So when a signal is going from low to high, so this is low to high propagation delay. Then we have tau P HL. This is high to low propagation delay. Then there is average propagation delay, which is given by tau P. Okay, let me write tau P. So tau P will be average of the two. So you take the average between the two, that will give you average propagation delay. Then I also told you we have a rise time and a fall time also associated. So these are all the propagation delay definitions. Okay. So these are the two input output waveforms of a typical inverter and the definitions of the delay times. So now let me just explain you in a brief. So this is my input step, ideal and a practical case. In a practical case, we have some finite rise time and fall time. So it starts with VOL, okay, goes to 50% and reaches to VOH. So VOH and VOL are the output high and the low levels. So it's defined for the inverter. For some inverters, VOL is zero. For a resistive load, VOL is not zero. For some inverters, VOH is equal to VDD. For resistive load and CMOS inverter, it is equal to VDD. All right. So here we have estimated the output. So it is in response to the input. The whenever the input is zero, the output is logic one, and whenever the input is going from one to zero, the output goes from logic one to zero. But it takes a finite time. Okay. And again, when there is a switching, when the input goes from one to zero, the output goes from zero to one. Again, it takes a finite time. So we need to measure this finite time. So now let's go with the definition. So propagation delay times are tau p HL and tau p LH will determine the input to output signal delay during high to low and low to high transitions respectively. So according to this waveform, what is the propagation delay given by? So when the input has crossed 50%, how much time the output takes to cross 50%? That much is the propagation delay. So according to this diagram, what is the propagation delay? What is tau p HL? Tau p HL is T1 minus T naught. Okay, so this is equal to T1 minus T naught. So how much time the output takes to reach 50% when the input has reached 50%? So that's the reference. So input has reached 50% at T naught and output has reached 50% at T1. Okay. Similarly, the low to high propagation delay will be given by, because the output signal is changing from lower value to higher value. That's why it's called as a low to high propagation delay. Okay. So by the time the output reaches 50%, and how much time the output takes to reach 50% value. So that is the amount of delay. So this is will be T3 minus T2. Agree? So T2 is the time when the input reaches 50% and T3 is the time when output reaches 50%. So ideally for the designs, this both propagation delays should be equal so that the analysis further will be simpler. But many a times these two are not equal. That's why we take the average value. So tau p will be tau p HL plus tau p LH divided by 2. All right. Okay. So average propagation delay will be the average time required for the input signal to propagate through an inverter. Now we have a rise time definition also, rise time and fall time. Can anyone tell me how much is the rise time? Rise time is denoted by tau rise. So the time it takes for the output to reach from 90% value to the fall time, rise time will be from 10% value to 90%. So it will be how much rise time? Anyone? TD minus TC, correct? From year to year. And fall time will be how much time it takes for the output to fall from 90% to 10% of its value. So tau fall will be TB minus TA. Okay? Understanding this, everyone, students? Did you understood the definitions? If they ask you in the exam, define the propagation delay associated with CMOS inverter with the timing diagrams, you have to explain this as it is. Now our aim is to derive an expression for tau PLH and tau PHL. There are two techniques. One is the exact method and one is the average current method. So let's go to it. Any doubts so far? Anyone? Students, do you have any doubts before I go ahead? Yeah. I know. I mean, there is one thing which I want to point out at the start. These topics are present in the syllabus. I agree on that. But these topics have, the frequency at which these topics are asked in the final exams are pretty less. So the question was asked in paper 2022 ESE exam. So maybe after every alternate or every 2 years they ask a question on this. But it's my duty to cover these topics. That's why we are having this lecture today. Okay. So there are two techniques. Now we have to find the expression for tau PHL and tau PLH. So there are two techniques. One is average current approach, which is an approximate approach, which will give you an answer very fast. That other matter is exact method by solving the differential equation approach. So you'll be doing both of them, and you can expect some numericals in exam from this topic also. So can we start with the average current approach, everyone? Can you give me a feedback? Yes, no, what? So that I can proceed. Okay. So first we'll start with the average current approach. So this approach is based upon estimating the average capacitance current during the charge up and charge down phases. So as I already informed you all, so we have a CMOS inverter. So this is my V in over here. This is my output, and we'll consider a single load capacitance to analyze the circuit. So now we determine how much time the capacitance takes to charge up to VDD and how much time it takes to discharge to the ground. So this is the charging time and this is the discharging time. And accordingly we'll calculate the average current and that will give us the average propagation delay. So it is based on estimating the average capacitance current during the charge down and charge up phases. So if the capacitance current during an on transition, during an output transition is approximated by a constant average current, the delay time can be found as follows. C will be equal to tau PLH will be equal to C load into delta high to low, that is the voltage changing from high to low, upon I average from high to low. So this is assuming that the output transition is having by a constant average current. Okay, a capacitance current during an output transition is approximated by a constant average current. So they are saying that whenever this is charging, there will be a constant current flowing through the capacitances. Yeah. So this is how they are given by. Now delta VHL will be given by VOH minus V50%, and delta LH will be given by V50% minus VOL. So for a CMOS inverter, VOH is VDD, VOL is 0. For the timing, we have written it for general expressions. It can be applicable for a resistive load inverter also. So now the average current during high to low transition, that is high to low transition, can be calculated by using the current values at the beginning and the end of the transitions. Okay. So where this formula came from, anyone has any idea? So do you remember this? What is the current flowing through the capacitance formula given by anyone? IC is equal to. Have you heard of this C dV by dt? charging current, I mean current through the capacitance is given by C dV by dt. Yes or no? Hello. Can you all at least, yeah, get this dt is my average, the time, tau. So if I write the same formula as dt is equal to C dV by IC. So don't you agree this is the same formula? dV is the change in the voltage. This is delta V. Okay. This IC is my average current from high to low. And dt is my tau, tau P HL. So it's not a different formula which we are not seeing. This is tau P HL or LH. Okay. So any doubts in equation number 1 and 2? Yeah. Now we have to estimate the formula for I average high to low and I average low to high. Okay. So to estimate it, we will calculate the current at the beginning, at the end of the transition. So it will be half of IC when V in is equal to VOH and V out is equal to VOH, and IC at V in equal to VOH and V out is equal to 50%. Okay. So whenever V in is high and the output is over here VOH and here the output is 50%, and we take the average of it, half of it. So this is how the I average high to low formula is, expression is. Similarly, we will find the average current during low to high transition. Okay. So here the input is low and the output is high. Here see, here the input is high, and when the output reaches 50% of the value from high to 50%, and here it is from 50% to low VOL. So this is the two formulas which are there. This method is relatively simple, but it is not very accurate. It is, the important thing to notice, it is not at all accurate to solve with this formula, with these expressions. All right. Okay. One second. Okay, now we might solve a numerical to understand this example. Uh, so this formulas we'll use in practice, and then we can actually understand what exactly and how to use this average capacitor current method. So can we find out first this form, or should I cover both the derivations and then I'll find the formula? Then we'll go to the numerical. What we want to do? Tell me. So I've given the expressions for the average current approach. So these are the four formulas with which you can solve the numerical. Or should I cover the other one and then go to the numerical? What do you say? Everyone? Tell me, shall I cover the numerical now or okay. So let us first cover a numerical. So let me show you the statement, and then you can, we'll go to the other derivation first. First let us understand. Yeah, this is the numerical statement. For a CMOS inverter, VDD is 5 volt. So let me open another PDF and keep. Yeah, let me just use this PDF itself. So for a CMOS inverter, VDD is 5 volt. Okay. So use both average current method and differential equation method for finding T fall. T fall is from 90% to 10%. The output load capacitance is 1 picofarad. So basically this is my CL. Okay, or C load, whatever we call that. So we can call this as CL, which is 1 picofarad. 1 into 10 is to minus 12 farad. VDD is 5 volt. The transistor parameters are given. So mu1 Cox is given, W by L is given. So that means Kn is given. Threshold voltage is 1 volt. Kn is mu and Cox W by L. That will be 20 micro into 10. Okay. Fall time is defined as the time elapsed between the time point at which V out is 90%, 4.5 volt, 90% of 5 volt is 4.5, and the time at which 10%. Okay, so not only the propagation delay from 50% to 10%, in this formulas which we have seen, it can be adjusted to 10% of for 90% also. So right now this is the propagation delay from 50% value to the low value, but it can be that can be adjusted to for the higher rise time and fall time also. So according to this formula we will adjust it. So I average HL will be half of IC, the current, the average value of it when V in is high. V in is VOH is 5 volt, because for a CMOS inverter VOH is VDD, which is 5 volt, and VOL is 0 volt. Okay, so this is 5 volt when output has reached to 90% of the value, that is 4.5, and when the input is 5, when output has reached to 5%, 0.5%, so from 4.5 to 0.5%. Okay, so we need to find this thing. So here when the input and output, now as we know that for the CMOS inverter, uh, when the output is at 4.5, that means we know that voltage transfer characteristics, right? Here it is. We have done, we have analyzed this technique. So this is V out versus V in. Okay, so in this case, this is not, let me just rub it out. So the first case, my transistor is in saturation, so that's why we have written the formula half Kn V in. V in is basically VGS minus VT and the whole square. Now how do you know transistor is in saturation? So basically V out, the NMOS, V out is basically your what we can say, let me draw it and show it to you. So if this is my CMOS inverter, this is CL, this is my lower transistor is my NMOS. So this is my NMOS and this is V in. Okay, so when my output is at around 4.5 volt, that means VDS is 4.5. Okay, VDS 4.5, and VGS is V in, which is again 5 volt. So how much is my VT? 1 volt. So VDS, for it to be in saturation, VDS has to be greater than or equal to VGS minus VT. It is so. This is 4.5. This is 5 minus 1. This is 4 volt, right? So my NMOS is in saturation. Okay, the one of the, let's say, the discharging period from high to low. Okay, so when your output is going from a higher value to lower value, then my NMOS comes into picture, and similarly here also your output is less, so it will be in the linear region of operation. So for linear region it is half Kn twice, here instead of VGS we have written V in, because for a NMOS transistor your VGS would be equal to V in. Okay, let me, the writing pad is creating some trouble. Let me connect it again, and so it hopefully it should work. Yeah, so this is nothing but VGS N. This is also VGS N, and this is actually VDS N. This is actually VDS N, which is equal to V out. All right, so we have substituted the values, Kn values available. It is 20 micro into 10. V in is available, that is 5, which is equal to 5 volt over here, and this is 1. And here also we have taken this half out, and we got the current somehow as 0.9875 after calculation. So do you wish to calculation, or do you will manage on your own, or I only discuss the solution? Everyone, do you want to write this, or should you just have a look at it? Hello, no need for calculation, sir. Okay, yeah, agree, I agree. So now the fall time can be calculated as C into dV, that is changing from 4.5 90% to 10%. The C value is 1 into picofarad and the average value. So we got the fall time as around 4.05 nanoseconds. This is the first case. Okay, this I think the fall time is meaning when the output is reaching from this thing from 90% value to 10% value. Alright, so in that case my NMOS transistor is active. So that means my capacitor is discharging. Now why we have not considered a PMOS transistor? Obviously because this is the discharging phase. Okay, that's why we have considered only the NMOS transistor. If it was a charging phase, we would have considered the other case. Okay, got it? So this is how you got the answer 4.05 nanoseconds quickly. So this is how we use this technique. I hope you have understood now. So if it is for a charging phase or a propagation delay, we need to calculate for both the phases. So there you need to do it for PMOS also. For PMOS, VDS will be V out minus VDD and VGS will be V in minus VDD. So that you have to take care. So this is how you calculate a delay time, that is a fall time delay here. Now let me go to the other technique. Yeah, this is the exact approach. This we will get the exact formula for tau p LH and tau p HL. So this is what we use in the design of CMOS inverter also. So we have to look at it. So give complete attention for 10 minutes. It will be completed. So we already know the CMOS inverter, right? So I am not drawing it again and again. I am drawing it for the one last time over here. So we have a CMOS inverter whose output is driven by a capacitive load CL. It is a lumped capacitance. Alright. So the propagation delay time can be found more accurately by solving the differential equation at the output node in time domain. So basically here we are writing the same thing. IC is C dV by dt. So here we have a current which is flowing here like this. This is IDN and the current which is charging up. So this is called as IDP. That's why we write IC, the charging current as, the current through the capacitor CL as IDP minus IDN. Alright? Because they are opposite. Similar signs but opposite. So IDP minus IDN. Okay, so current, again the charging current is given by C dV by dt. So we have written C, this is called as C load. So C load dV out by dt is equal to IC. Now we consider the rising input case. So when the input is rising means it's going from VOL to VOH. The output should go from high to low. Yes or no? When the output goes from high to low, that means it is in the discharging phase. So we are in the discharging phase now. So for a discharging phase, which normally transistor is on? NMOS is on. We are in the discharging phase. Okay, so that's what we consider only the lower part of the circuit. So let's say the capacitor is already charged to VDD, and now the discharging takes place in this fashion. IDN. The charging current is IDN. So this is the equivalent circuit of the CMOS inverter during a high to low transition. Okay. So initially the output is assumed to be VOH. As I already told you, the output is assumed to be VOH, which is equal to VDD for a CMOS inverter. So when the input switches from low value to a high value, the NMOS is turned on and it starts to discharge. As I already told you, the NMOS turns on and it starts to discharge. At the same time, the PMOS is off. Okay, so IDP is equal to 0. Agree? So the differential equation describing the discharge event will be CL into d V out by dt is equal to minus IDN. Agree up till here? Yeah, because IDP will be 0 because PMOS is turned off because it is discharging event. So charging event is turned off. Okay. So now we consider this case. So input is going from VOL to VOH from low to high. So output will go from high to low. As I already told you, it will take some time. So let's say it starts with VOH, which is actually equal to VDD. and it goes down. Okay, so it goes to VOH, then it goes to minus VTN. What is this minus VTN? Let's say that VTN voltage is how much? Let's say 1 volt and VDD is 5 volt. So this voltage will be VDD minus VTN, which will be 4 volt. So this will be somewhere around 4 volt, let's say. And this is 50%. Let's take some numbers. So if VDD is 5, 50% value will be 2.5 volt, for example. Okay. So we already know the reason over here. From VOH to the 4 volt, from 5 volt to 4 volt, my NMOS will be in saturation, and after that it will be in the linear region. Now this I will make it more clear by putting some numbers. So as input goes from low to high, NMOS is fully on and PMOS is off. Therefore the capacitor CL discharges via NMOS transistor. But the NMOS transistor, when it is on, it can be in two regions of operation, right? One is saturation, one is linear. So as the output falls, the CL is discharging. So this diagram is important. Please have a look at it when you do the derivation. So when the NMOS starts conducting, it initially operates in the saturation region. Okay, because the output voltage is high, and when the output voltage becomes low, then it goes into linear region. So for example, here output is at VDD, which is 5. Okay, and input has input is VGS, right? So here it is. Input is just changing. Input is going from 0 to 1. So it has reached already 1, and now the output is changing. So V in is actually reaching 5 volt now, and output is decreasing now from 5 volt to 0. Okay, so currently we have VGS equal to 5 volt, VDS equal to 5 volt. So I have already shown you VGS should be VDS should be greater than VGS minus VTH or VTN, which is 4 volt. So that is correct. Now when the output falls to 4 volt, so V out is 4 volt now. Okay, that is equal to VDS. So now VDS will be VGS minus VTN. Let's say this VGS is 5 volt and this VTN is 1 volt. So this is 4 and this is also 4. So we have reached the edge of saturation. So beyond that, if I go, this VDS will become less than 4. So if it becomes less than, even if it give him 3.9, that means VDS is less than VGS minus VTS. That means my NMOS operates in the linear mode. So NMOS operates, yeah, just a second. Yeah. So you're understanding, right? So why I have written over there at VTN value. Okay. So whatever the VTN value is, maybe it's zero point 0.5 or 1 volt. I've explained this example with 1 volt. So as the output, this is output actually. So whenever the output goes below this VTN value, then my NMOS goes into linear mode of operation. Understood this? This is very, very important to understand when is NMOS is in saturation, when is NMOS is in linear region. Understood this? Yes, no? Yeah? Can you just, at least respond yes or no? Because I am the only one speaking, so I don't understand whether you're following or no. So whenever the output voltage falls below VDD minus VT and the NMOS transistor goes into linear region. Yes? Okay. So we'll first consider the NMOS transistor operating in saturation. So IDN will be Kn by 2 V in minus VTN square. Okay. So this will be between VOH. So output is between VOH and VH minus VOH minus VTN. VOH is nothing but V out. So in this range, as I already told you, this is VDD and this will be VDD minus VTN. Okay. So V out is less than 5 but greater than 4 volt. Example. Okay. So IDN is practically independent of output voltage in this. So the solution for equation number 2 is the time interval between T0 to T1 dash. So here it is. We have to calculate in this interval, right? T0 to T1 dash. So during this period, the NMOS is in saturation. So we can integrate and find the area, and then we can find the result. So dt is going from integral from t naught to t1 dash, and here it is minus C load. C load is a constant, capacitance is a constant, where V out is going from V out VOH to VOH minus VTN, dV out by IDN. Okay, so here we substitute the formula, IDN formula. IDN is what? Kn into, what is it, half, right? What is IDN now? Half kn by 2 VOH minus VTN, because Vin is VOH, right, in this case. So it is kn into VOH minus VTN the whole square. So this half will go up, so this will become 2 C load. So here it goes from, if we open the integrals, it will be T1 dash minus T naught is equal to twice C load VTN upon Kn into VOH minus VTN square. So you understood equation number 5? So this is where the NMOS is in saturation. Now we go for NMOS is in linear region. So that will be when output is less than or equal to VDD minus VTN. So in that case, it goes into linear region. So the formula is Kn by 2 twice V in minus Vtn into V out minus V out square, where V in is VOH. Okay. So the solution for equation number 2 is the time interval between, here it is 6, yeah, equation number 2, sorry, from above. Let me show you equation number 2. This equation number 2. Okay. So for that equation will be, how we got that, actually we have written that now id is equal to, where it was, let me write, yeah. So here what we do is we consider dt, and on this side we consider c dv out by idn minus of c load. You can consider minus over here or there. So this equation we integrate. Okay, dt we take it on that side. So now we continue the same thing, but we continue till 50% value. Okay, so V out, when it goes from let's say this is VDD to VTN, that is 4 volt to 50% or 2.5 volt. Yes or no? So if, for example, so this is from T1 dash to T1. Let me show it to you. So from T1 dash to T1, this is the formula. So T1 is 50% value. Okay, so V out is between, actually this is the interval for V out less than or equal to VDD minus VTN, and greater than V of 50%. Okay, so we have estimate the same thing. So we apply the formula over here, twice K CL will come out, C load will come out. So Kn twice VOH, V in is VOH, right? This formula will remain as it is. Okay, and it will be dV out. Now evaluating this integral will lead to this. So you can check it out how this has come. You can again it will be integration by limits, and this integration after solving you will get this result. Okay, so it will be minus twice C load upon Kn, 1 upon twice VOH minus VTN, natural log of 1 upon V out upon twice VOH minus VTN minus V out. So in this we put the integral limits as VOH equal to VOH minus VTL, and V out is equal to 50% value. Okay. So here we put the limits and we get this equation number 7. So T1 minus T1 dash will be equal to this. So you can put the values and find out the answer. Okay, V out. Instead of V out, you substitute this results, you will get this formula. Okay. Now tau p HL will be this T1 dash minus T naught plus T1 minus T1 dash. So V 50% value will be half of VOH plus VOL. Yes or no? So it will be 50% value will be VDD plus 0, VDD by 2, right? So now the tau p HL will be this now. So this is the result for this one, 50% value you substitute now. So half of VOH minus VOL, you substitute in this formula. So tau P HL will be C load. So C load Kn VOH minus VTN. Here it is. Into twice VOH minus VTN. Here it is. So from the earlier result we have got twice VTN upon Kn into VOH minus VTN the whole square. So we have taken this Kn into VOH minus VTN the whole this thing out. So this is what we get by combining equation number 5 and 7. Okay, so this is a result of combining 5 and 7. We modified further. Here we cancel out the terms. So here we cross multiply, so we'll get twice 4 times VOH minus VTN, and here it will be minus 1. So we get equation number A. Now for a CMOS inverter, we know that VOH is VDD and VOL is 0. So equation number A will become this. Equation number 8. So this is what we substituted for. Alright. So this is the formula which we have used in our lab also for estimating the delay, the propagation delay, the high to low propagation delay. So this is what we arrive at. Equation number 8. C load upon Kn VDD minus VTN, this formula. Alright. And if we substitute this tau n as Rn into C load, so let's say Rn is 1 upon Kn VDD minus VTN, so we can simplify this formula as follows. So in a CMOS, so this is the charge down event, that is when this NMOS is discharging. Okay, exactly in the same fashion, the NMOS will be charging also, the PMOS will be discharging. So if we have a CMOS inverter, V in, V out, we have a capacitor. So now we are considering the charge up event. So in that case, PMOS transistor will be considered. Okay. So it's completely, the charge up event is completely analogous to charge down event. Okay. So here I guess I have to rotate. Yeah. So this is the thing which we have to do for charge up when input switches from high to low. So similarly you can carry out the derivations. So similarly you will get this result. We are not supposed to do this in the exam also. If they ask you, we can directly write the result, this one. Okay, so this is tau P LH is C load upon Kp, because it is for PMOS transistor. As you can see, it is written VTP mod of, because it is negative. So equation number 10 you get it. Equation number B is generalized formula, even valid for resistive load. For equation number 10 is for only for CMOS inverter. So once we know the high to low and low to high propagation delay, we find the average propagation delay. Alright. So you go through those derivations. If you face any problem, then you let us know. Okay, I have to change to orientation. Yeah. So then we'll come back to this numerical, and we can solve this via the technique. So right now the saturation region is between 4 to 4.5 volt. So here they have written it, and so after solving it in that equation, they got it as 3.69. So you can go by this technique, it's more accurate, whereas by average method we got it 4.09. So it's quite a deviation, nearby but quite a deviation. Okay, good. So I hope you can note down the formula for tau P HL and tau P LH. Not now, but later on, because these will be required for design of CMOS inverter. Okay, so design of CMOS inverter is another question which is of importance. So with delay constraints. So the design of CMOS inverter is based upon the timing delays, which is one of the most fundamental issue in digital circuit, which will ultimately decide the performance of the complex circuit. So your CMOS inverter design is based on timing constraint, that is tau, fall time, rise time, propagation delay time. So basically this is my CMOS inverter. For CMOS inverter designing, we should design the W by L ratio. So W by L of P, W by L of N, then C load and V in. So the basic goal of the design is to determine the dimensions Wn and Wp, because L will be known to you. L is a technological constant. So now given a desired delay value, let's say as a application we have been given a desired delay value, okay, tau p HL. So W by L ratio can be found out as follows. So remember in that formula, let me show it to you one more time. We can have W by L ratio also over here, right? How? Kn, na? Kn, what is Kn? Mu n Cox W by L of n. So if I substitute W by L over here, I can write the same formula as W by L, and then it will be C load upon mu n Cox tau p HL. So same formula can be modified as follows then, if requirement of delay is there. So that's what we have done over here. Just have a look at it. See this. This term has come down because this is the design requirement now, and we have to design the CMOS inverter. That means we have to find Wn. Ln will be given to you, so it will be C load tau p HL mu n Cox. No need to remember this because this is the same formula. And similarly, the W by L ratio of PMOS can be found out by using this formula. So delay constraints plus design constraints will be such that the noise margin, logic levels, silicon area, and power dissipation. Alright, so these things we need to consider. Yeah, so now we come to a very important design. We will go through it step by step actually. Okay, you all are there with me? Just this is an important this thing. I think you all don't have this PDF right with you right now, or it has been shared with your by your friends. No, na. I will share it. Yeah. So explanation was missing. So that is what we are discussing over here. Okay. So now this is a very important design numerical. Now let's go through it. It's the same. This I have written in wordings. Same, almost same. I think. Yeah, it is same. The parameters are also given. Let me cross check. Yes. So we have to design this numerical. Let us understand it. Let us spend 10 minutes time to understand this numerical. So please pay attention because it is quite important. So mu and Cox is given. This is for NMOS. This is for PMOS. L is given. I already told you L is the technological length. So basically this L is nothing but okay, this L is nothing but Ln and Lp, which is equal to zero point 0.6 micrometer. We can convert it into centimeters. Then VTN is given, VTOP is given. It's asymmetric inverter because those both are different, and W minimum is given. Means the minimum value cannot be below this. Okay, that's the requirement. So we have to design a CMOS inverter by determining the width WN, the channel width WN and WP of the NMOS and PMOS to meet the following performance specification. This is very important. If you go in a technical interview of a VLSI job, they will be asking you this question. What are the performance specifications? The performance specs are VTH should be 1.5 volt. VDD should be 3 volt. That means uh, what I am saying is if I have a VTC curve and if I have this uh, okay, so this is V out, sorry, this is V in, this is V out. So if I have a line passing through the origin with a slope 1, wherever it intersects, this is VTH. Okay, this is the switching threshold voltage of the inverter. This is VTH, switching threshold voltage, and this is V out equal to V in line. So they are saying that this should be at the center. If this is 3.3 volt, this should be 1.5 volt. Actually, nearby it should be VDD by 2. So we want it close to VDD by 2 only. Alright. So this is one of the design constraints. Sorry. And then they have given that your propagation delay times tau p HL should be less than or equal to zero point 0.2 nanoseconds. It cannot be greater. It has to be less than this, and tau p LH should be less than or equal to 0.15 nanoseconds. So this is the design requirements given to you already. So and the third is a falling delay of 0.35 nanoseconds for an output transition from 2 to 0.5 volt. So a falling delay, fall time we have given. So we have to also have a look at it. Then the C load capacitance value is given to you as 300 femtofarad. Okay, so the C load is 300 femtofarad value. All right. So can did you understand the numerical what we need to find out? So we need to design the CMOS inverter. Now, what do you mean by designing a CMOS inverter? You will say, so all the requirements have been given. This is CL. Designing CMOS inverter means we have to find W by L of P, W by L of N. So here Ln and Lp are already given, which is around how much? Uh, zero point 0.6 micrometer. So we need to find Wp and Wn such that it satisfies all these three requirements. Uh, Constraint number 1, constraint number 2, and constraint number 3. Understood this? So designing means we have to find the value of widths of PMOS inverter and NMOS inverter. Are you understanding? Yeah. So we start the design by satisfying the time delay constraint, that is tau p HL and tau p LH. Just now we have derived the equation, so we will see Wn by the Wn by Ln, that is W by L of n. Actually we can write it as W by L of n for NMOS is given by this formula. Plug in the value, C load value, tau p HL value is zero point 0.2 nanoseconds, mu1 value is 120, mu1 Cox is 120 micro, VDD is 3, VTN is zero point 0.8. So plug in all the values, you will get it as uh, 7.9. W by L of n will be 7.9. Okay. Similarly, W by L of P we can calculate by using this formula. It comes out to be 25.2. Okay. So we got the value of W by L of n and W by L of p for the first constraint, for the second constraint actually. Okay. Now, during the falling output transition, that means the VDS is falling, right? When the output is falling means what? VDS, that is for the NMOS. So VDS is falling from 2 volt to 2.5, from 2 volt to zero point 0.5 volt. Yes or no? So during the falling output transition of from 2 volt to zero point 0.5 volt, the NMOS transistor of the CMOS inverter will operate in the linear region. How? How this is possible? Why it is in the linear region? Can anyone tell me now? Yeah. For a CMOS inverter, for a falling transition, this is VDD, this is ground, this is NMOS, and at the output you have this capacitor. So they are saying when the output is falling down from a higher value to a lower value, let's say it's falling down during the output transition of 2 volt to 5 volt. So when the output is going from 2 volt to 5 volt, that means your V out of N is VDS N, right? So VDS is going from 2 volt to zero point 0.5 volt. Okay. During that time, what is my input? Input is at VDD, right? So here input is equal to VGS N is equal to 3 volt. Okay. So VGS is 3 volt, and now how much is VTN given to you? Is zero point 0.8. So VTN value is 0.8 volt. So when is the transistor linear? So VDS N should be VGS N minus VTN. So this is how much? Let's say this is 2 volt. VGS N is 3 volt, and this is zero point 0.8. So 2 volt is less than that, right? Yes or no? It's less. Now this is more, right? So my NMOS is in linear mode of operation. Understood this, everyone? So that's why my NMOS is in linear mode of operation. So the current equation of the transistor will be, so this will be equated as ID linear, ID and linear is equal to C dV out by dt, minus of ID linear is equal to C dV out by dt, CL times. Okay, that is what we have integrated. So it is half mu n C ox W by L twice VOH. You understand why VOH, right? Because it is VGS. VGS minus VTN into, this is V out. This is VGS, this is VDS, this is VDS, N of the NMOS. Okay, so this we substitute the values over here. Then delay time is given as how much? 0.35. So equate we delay time as 0.35, and we solve within the limits of 2 to zero point 0.5 volt. So we plug in the values over here, okay, t delay time over here, and somehow we got that equation. W by L of n is unknown to you, right? So solving this, we got W by L of n as, or W by L of n as 6.1. Okay, so integrating is a little tedious, but we have to do it over here. So W by L of n is 6.1, and here we also already got W by L of n is 7.9. So which one to consider? Tell me, we have got two W by L. So earlier we got W by L of n as how much? 7.9. So which one to consider? So notice that this ratio of W by L, that is 6.1, is smaller, found from the propagation delay. Thus we take the larger ratio to satisfy. So both the timing constraint. In order to satisfy both the timing constraint, we consider the larger ratio. Okay, and determine the size of the transistor. So we determine, here it is 7.9, L is given as zero point 0.6, so Wn will be how much? So Wn divided by zero point 0.6 micrometer is 7.9. So here Wn is found out to be 4.7 micrometer. You can check it. Okay. Next, the logic threshold constraint is this. VTH is 1.5 volt, right? So which will help determine the PMOS transition. So VTH is given by the formula. This we have already know, right? This formula. Okay. So this is given as for 1.5 volt. Now we find the inverter ratio as per this. We rearrange the terms. We got it as. So what is the inverter ratio given by? Okay. So from here we calculate KR. So from here we calculated KR, and KR was found to be 0.51. Now KR is what? KR is given inverter ratio, which is Kn by Kp. Kn is mu n Cox W by L. Here it is. And Kp is mu n Up Cox W by L. So we substitute the values of Wn and Wp, which is 7.9, and Wp by Wl. So here we got Wp by Wp by Lp as 31, and earlier we got it as 25.2. So we consider a larger ratio. So we consider this one, this ratio 31. Okay, so larger ratio will satisfy both the timing constraint and the VTH constraint. So now we determine the PMOS size as how much? So WP will be 31 times LP, which is 31 times 0.6 micro meter. Yes, it is zero point 0.6 micrometer. Yeah, so that is what we get. WPS 18.6 micrometer for the given LPS. So hence the designed inverter will be as follows. Okay, so you draw the inverter with the timing constraint. So basically W by L ratio we have to find out. So this is CL. So finally the designed circuit will be the design CMOS inverter. So here W by L of N will be how much? We have considered 7.9. So this is 7.9, and W by L of P will be 31. Is 31. So this is the design circuit. All right. So I think this was an important numerical, as you can see, signify. Depending upon the constraints, they might give you this. We have to design an inverter around the constraints. Okay, this is the same given over here. Okay, it's the same numerical. All right. So that's it.